Thank you, Hilton. Does everyone hear me all right? No. I got to turn this thing on then, maybe. I got to speak into it. Is this a little better? No, still no. Louder. How's that? All right. I made it. So as Hilton said, I'm the instrument master for MOSFIRE. I've been with the project essentially since it's commissioned at the observatory, and so tonight I'm going to talk to you about my experiences with the instrument, some of the fabulous science that's being done with some of our astronomers, and hopefully, well, you know, I was just at a science fair. I was a judge at a science fair this afternoon, and one of the things that I really like when I see some of these students talking is I like to see them present something new, even if it's not they haven't gotten all the ideas about how they form their science or how they put it together. But if they come up with a new concept, that's what I really like to see. So hopefully, I'm going to give you something new, because that's what I think is important when we're sharing this stuff. So first, right off the bat, we're going to talk about the guys that were involved with this. Hilton has already mentioned this great team. MOSFIRE is very unique in the sense that we had this collaborative effort with an instrument. Normally, a lot of the instruments that are built for the Keck Observatory have been built by individual institutions. But in this case, we had a very collaborative project where Chuck Steidel at Caltech led the Caltech side. Ian McLean was at UCLA. But we also had partners at the University of Santa Cruz who worked on some of the optics, and as well as the rotator. So this big instrument actually rotates around. It's, you know, it's rather big. It's like the size of a small car. So in the upper right, we've got their team, and that's right when they were about to ship it. So that big crate that you see right behind them, that's MOSFIRE encapsulated in its shipping container. So it's about to go on a boat. And then we obviously can't acknowledge all the efforts with MOSFIRE without the contributions of Gordon and Betty Moore. So we also got Gordon's first visit to the instrument, I believe, which was in, let's see, when was that? That was in September. What do I got here? I got to scroll down in my notes. Oh, sorry. Oh, I've already messed up. I'm way ahead now. So, MOSFIRE arrived at the observatory on the 16th of February in 2012. That's essentially when I take over. So you'll notice me in any of these pictures. I'm the guy in the brown suit. I don't like being cold at the summit, and so that thing's insulated. Keep me nice and warm. MOSFIRE arrived in that big crate. We've stripped it off because it wouldn't fit through the doors at the observatory. And it's got this Mylar bag sitting around it with shrink wrap around it. The image on the right is where we're actually inspecting the electronics and making sure everything was nice and safe. And then lower left there is the instrument as it's about to be, well, it was just craned up to the top level of where it sits in what we consider the train yard at the observatory. Ian McLean was very nervous about that, but we've done that lots of times, so it wasn't really that much of a problem. April 4th, 2012, that's when we were ready to install. I was not on the summit that day, so this was taken by a few members of the MOSFIRE team. This is an image that shows MOSFIRE going into the back of the telescope, and although we were ready to go for first light, we weren't quite ready with the instrument. If you notice right over here, we've got ratchet straps. That's like the number one thing at the observatory to make sure everything's secure. And we got a C-clamp there to keep it from rolling off the front of its transfer module. Most of the instruments and MOSFIRE now is not like that anymore. But the first night, we made all the stops to try and get it on the telescope. So if you get up there, you'll notice that it's secured most like the rest of the instruments. And this is the standard first light image. So MOSFIRE was commissioned on April 4th. I was a part of that process. I was, in particular, in charge of making sure when we were pointed on sky, we were pointed at the right spot, and we had all the angles calculated correctly. So this is actually MOSFIRE's third light image. The first light image was just a star. And we all decided, and you can see this in my log entry, from that night, we acquired the first light image was actually of NGC 5053. This is your backstage pass now. You're getting to see some stuff. And the antenna galaxy was just cooler. So this is actually the image that I put together later on. I actually have this now hanging up in my office. I hope to have Ian and Chuck sign it someday. That's my memento. But this basically catches you up on MOSFIRE, all right? So Ian and Chuck, they've talked about this. You may have seen them talk about MOSFIRE in the past. Other people who've also been involved with MOSFIRE in terms of their data taking and their science, they've talked about the instrument. And this essentially brings you up to date in terms of what they've presented. So here's a little tidbit from our instrument commissioning process. And if you get up to the summit, I hope you'll take a look at the back of MOSFIRE. What you're looking at here is the telescope structure. Here's me and our summit lead, Grant. And then over here we have Tomas. He's climbed up on the structure. And he's taking a look at MOSFIRE. We actually have the doors off the electronics cabinet. And what's happening here is we're swinging MOSFIRE for the first time past the yoke in the telescope structure. And it fit great. You can see right here, here's the orientation of it. Well, turned out if we rotated it 45 degrees, we wound up hitting the bolts on the telescope. So here's the corner of the cabinet, and here are the bolt heads on that yoke, those two I-beams that were kind of meshed right there in the yoke. And so this is the reason. If you get up there, you're going to notice that on the back of the MOSFIRE cabinet, these corners are rounded. So you can talk about that with some of the people up there. And I want you to keep an eye on this guy. This is Alan. Alan's first week on the job, he was cutting corners. Oh, that's terrible, I know. That's terrible. So, after first light, let's see. We're just going to talk quickly. Let's see. Debbie out there wanted me to put in some nice photos. So this is actually one of my favorite ones, becoming one of my favorite ones. And the reason for this is it reminds me of when I was a graduate student working at the IRTF. Hilton mentioned that I commissioned an instrument back there. So the IRTF, just for everybody's information, is the small telescope located as close to Keck, if you've been up there on the ridge. So here's Keck I and Keck II. There's the IRTF. And when I would come out of the IRTF in the morning, so after observing all night, especially after like 7 nights in a row, we'd wind up looking at the two Keck domes, and we'd see, sometimes we'd see the moon in between the two Keck domes, but more importantly, we'd see this little feature right here. This is the shadow of the mountain, if anybody's seen that up there. That's in the atmosphere. This is at sunset. So in sunrise, the shadow is in this direction, in between the two Keck domes. So that takes me back a little bit to my time there. And one of the things I remember distinctly about being at the IRTF and being in the morning like that is looking over those two Keck domes, and I'm wondering, what is happening over there? So fortunately, I got to come and see and be a part of it. This is another image of the two Keck domes. This is Keck II being opened up at night. Here's Keck I. MOSFIRE lives in here, in the Keck I area. There's actually 4 instruments there, so MOSFIRE shares time with the other instruments at night. There's LRIS, there's MOSFIRE, there's HIRIS, and there's OSIRIS. This is an image that was scrolling through earlier, but this is I just want to make sure everybody's clear on how MOSFIRE takes data. And so light comes in over here at the top. It bounces off the primary mirror. Then it bounces off the secondary mirror, and then we have a choice. We can either put a tertiary mirror in here, a third mirror, which bounces the light to instruments at the Naismith position, or we can take that mirror out and plug in an instrument. So MOSFIRE is one of these that gets plugged into the back of the telescope. And so now this image is us taking an image down the barrel of the telescope, looking back down at MOSFIRE. And you can see right now there's actually these train tracks that MOSFIRE rides in as it comes in. Here's LRIS. This is one of the other instruments that I was formerly in charge of. That's a sister instrument to MOSFIRE. So MOSFIRE works in the infrared. LRIS works in the optical light, so the light that our eyes can detect. And right where LRIS kind of starts to not be sensitive, MOSFIRE is starting to pick up. And so the people that have been doing their science with LRIS are now starting to do their science with MOSFIRE because they can do that now in the infrared. Just a few facts. MOSFIRE is our largest doer. And what I mean by that is MOSFIRE is a giant thermos you can't get into. All the optics, all the mechanics, everything that turns or moves, or even the detector has to be cold inside this instrument. And that's because if it was hot, the instrument and the detector would start detecting the heat from the optics and the mechanics that are a part of this instrument. So that would limit us in terms of our ability to see faint things on the sky. The other thing is that this instrument is the heaviest instrument at the observatory. I'm not sure it wants that distinction, but it is. It's about 5,400 pounds, and that's just what you see essentially in blue. That does not count this rotator around it or the transfer module itself. I think overall it winds up weighing around 10,000 pounds. And then once it gets put into the telescope, we have, these are the people that I observe with. So I want to give credit in some sense to the people that I work with. And these are two of them. This is Joel over here. And Doug. These are kind of our mountain men. And Joel has been instrumental in making sure that we continue to improve the instrument. So he's always good. If you want to know something critical, essentially, something that could be improved, you can go to Joel and ask him for his input. And then Doug is one of our night attendants, and he's up there all night long, and surprisingly, he has helped me quite a bit in terms of some of the MOSFIRE problems that we have found during the evenings. So he has helped me diagnose those things and solve them. But I just want to show you what my second office is at the observatory. This is me. This picture was taken in November, and this is my Movember goatee, for those of you who are men's health advocates. I actually had to start that in October. Here's Chuck. He's one of our instrument builders. This is Allison. She's a student of Chuck. I think she has graduated and gotten her PhD. They're ideally one of our frequent flyers with the instrument, especially Chuck, since he kind of deserves it after having built it for several years. But if you haven't visited remote ops, this is what you see when you come to the observatory, and this is where all the observers kind of do their work. I'm usually not sitting here. Most often, they're asking me to take the photo. So I'm off camera somewhere, and they're doing some nice action shot of them using the camera. But most of the time, they're talking to Joel over the Polycom or Doug over the Polycom. They're controlling the instrument here, and when they have questions at night, they ask me. Or at least they ask me for help. Chuck is, of course, one of the experts. We call them our black belt observers. But on occasion, and I develop things that are new, so I have to share those new developments with him. So he's still learning things. And so in terms of how we break things out at the observatory, our responsibility. So Hilton mentioned that I'm the MOSFIRE master. There are currently, 1, 2, 3, 4, 5, 6, 7 of us who are members of the Support Astronomer team. So I am in charge of MOSFIRE, but I can't do it alone. So I've got Jim, Scott, and Luca who are also helping with MOSFIRE, and that's because MOSFIRE is extremely popular. MOSFIRE gets 150 nights a year now. That was 2014. I can't stay up that long. My wife over there would probably be very upset with me. She's nodding her head. Thank you. And all these guys are on call 24/7. So you're not supposed to have your cell phones, but I'm just going to read you 2 texts. 6:40. Mark. This is from Scott. Mark, if you get a chance, I'm having a problem with MOSFIRE. Call me. Jim. No need to call Scott. I got it. That was at 7:05. So This is proof here. Astronomers are on call all the time. I can't believe I actually got a text from those two creatures. Anyway, so that was Jim, and that was Scott. Scott's working with the new observers for tonight. MOSFIRE is actually on Sky. There are actually 9 instruments at the observatory, and although I support and in charge of MOSFIRE, I'm actually helping observers with several different instruments. So I have to be trained on a lot of different things. And I don't mean, I know Randy's in the audience, and I don't mean to shortchange you, Randy. I realize the AO benches, there's 2 instruments there, but I have everybody's responsibilities here marked out. And although I have 2 and Jim has 2, I wanted to make sure that Randy got his due credit. So there's a lot of wealth in terms of knowledge and experience that's shared across this staff. And all of us are in charge to be the point person of various instruments. So although I'm up here today to talk to you about MOSFIRE, it could have been any one of us. So I just want to express that. And here are the great observers. So the previous slide, we are in charge of those instruments, and our goal, one of our main goals, our job description is to keep those instruments running as efficiently as possible. The observers are also part of our charges, and it is sometimes much more difficult to keep the observers running as efficiently as possible. But these are some of our most experienced observers, and when they fly in from all over the world, actually point out a few of them. Nick was actually 4 nights on the telescope last 4 nights. He finished his last night yesterday. Kristen and Greg Mace, they're some of our new and upcoming astronomers with MOSFIRE, and they are actually part of the instrument teams that built this fine instrument. You can see some of the other observers. Here's Alice. The nights are real long. We've got Carl over here. He's one of our new MOSFIRE observers. He's flying in all the way from Australia. So we have this very diverse group. They all have different programs, and it's my job to make sure that they can get the science that they want out of the instrument. And because their programs are diverse, the way we observe is not always the same. So one of the things I hope to do is tell you about their programs and what they're different. So these guys are all the experts in the field. These are guys are at the top rungs in terms of astronomy, the cream of the crop. They're coming in with the best science ideas and executing those science programs. I'm on the bottom rung. I'm going to admit that. But it's fun. I get to live vicariously, mostly through these guys. And although I'm on the bottom rung in terms of the science that goes on with the instrument, I am on the top rung when it comes to operating MOSFIRE. These guys don't have the chops when it comes to observing with this instrument. I'm number 1. So, here is our first observers. This is Alan and Jenny. They were UH. They were the only institution practically not to partner in the building of this thing, and they got the first time on the telescope with it. Jenny and Alan were extremely surprised at how well this instrument was performing. They were shocked. And part of the reason for this was that the instrument performance matched the predicted predictions. And so that graph over there on the right is showing you that MOSFIRE's prediction in terms of all by itself was this blue line. There's a black line buried in here that represents the MOSFIRE instrument plus the telescope performance. And then that red line on there is actually what we measured for a star. And it's perfect. Absolutely perfect. You couldn't ask for something better. So the observers have been pleased. We've been regularly observing with this instrument since 2012. And although we had that mechanical problem, MOSFIRE has been very, very smooth. I'm going to mention briefly its 2 claims to fame, why this instrument is so cool and awesome. MOSFIRE's first step forward in terms of technology was the cryogenic slit mask unit. And if you've seen a talk from Chuck or Ian, they've shown this slide. This is actually borrowed from one of Ian's presentations. But it's this giant mechanical slit mask making machine. with any of our instruments such as LRES or DEMOS. These are our optical multi-object spectrographs. Essentially, we take a cookie sheet and we cut some holes in it, and then we put it into the instrument and we take spectra. So instead of cutting holes in a cookie sheet, this thing creates a whole bunch of slits. So it's very nimble. This gives you an example of the size scale of the instrument and the CSU. So this is the CSU out of the instrument. This is the CSU in the instrument. This is Keith Matthews. I can't talk about MOSFIRE and its mechanical technologies without talking about Keith. Keith, actually, I believe this is, and Randy can probably confirm this for me, this is his 86th Dewar. So his 86th giant thermos, which is a testament to his instrument building capabilities. Hilton also mentioned that the telescope I worked with originally was about a 60-inch telescope. That's about the size of MOSFIRE itself. So clearly I've graduated. And this is what a deployed CSU looks like. So over here, if you look closely, it might be hard to see in the back, but there's these little boxes, and all these bars move back and forth. So when I talk about a bar, this mass can make 46 slits. And so what happens is a bar will move in from the right, a bar will move in from the left, and it'll create a slit. Then you've got 46 other pairs, and they can be positioned and deployed anywhere in the field. So you can look at a field, take an image, see which stars or galaxies you want it to take, and then configure a new mask. That's much faster than anybody else could do that. He can only go out to that. That's what LRES and DEMOS essentially cover. And he's been doing that using two emission lines from a galaxy, H beta and oxygen. So this is hydrogen and oxygen that he's been studying. But now he wants to extend his science to the infrared because he wants to look at things which are further out in the universe and slightly younger in terms of the look-back time. So when MOSFIRE comes along, it now covers this whole region in here. So it can look back to a Z of 4. Z is how we measure the redshift of an object. But essentially, he's looking back until the universe was about 1.5 to 2 billion years old. He's looking at K-band. And this is one of MOSFIRE's primary goals, is to take surveys that have been done in the optical and extend them out to the infrared, where these optical lines that they used to study, because these things are so far out in the universe, they're now redshifted into the infrared. So these boxes right here and the blue diamonds right there represent where hydrogen emission is at all these different redshifts. And because this is a redshift study, Brad actually didn't like this photo. He wanted his photo at a slightly different redshift. So there he is, and myself at a slightly earlier epoch. These are his results, and we don't need to get into the details of this. It's too much. But I'm going to briefly explain that these represent all the galaxies at a Z equals 0. So these are the galaxies that are our local neighbors. They don't create stars very fast, but there's a lot of them. When we look at objects at a Z equal 3, or roughly 1.5 times, or 1.5 billion years young, the star formation rates are really, really high. And these red dots represent where MOSFIRE has contributed to it, or at least in Brad's results. These images up here are from Hubble. They show us what the galaxies look like. They're really, really tiny. These are actually the spectra from MOSFIRE. And you'll note that although in the images these things are pretty much vertical, in the spectra they have a slight offset. And that's because those two galaxies have a different redshift. They're at different distances. So these two galaxies, one of them is over here and one of them is on the other side. I had to ask Brad that. I couldn't guess that just from the images. But I said, Brad, this is pretty cool. It's not bad. It doesn't really show MOSFIRE, but Brad was being coy with me. Turkey. These blue circles up here, and it's hard to see this in the back, but there are some open circles. Those are from Symphony on ESO. They measured 23 galaxies. It took them 180 hours to do that, and that's because they were doing it one object at a time. Brad, with MOSFIRE Keck, did 15 galaxies, one slit mask, in 10 hours. So he basically got about half of what they got. Now, what Brad didn't tell me, and what I had to find out for myself, is that those other points in this graph are also due to MOSFIRE. Dr. Richard Ellis measured those other galaxies. So what has happened here is that we've got 23 galaxies measured by this instrument and this observatory, and about 28 galaxies with this one. This has taken 20 hours, and this has taken 180 hours. So MOSFIRE is, in this case, 10 times more efficient. That's awesome. Yay, MOSFIRE! Let's hear it for MOSFIRE. All right. So the next advantage, so that is the multiplexing advantage with MOSFIRE. All right? Because you can do that and take a statistical sample, you can really do some cool stuff. So the second thing with MOSFIRE is that it had this new detector technology. It had the Hawaii 2RG, and we don't need to get into the details of that, but that's this new infrared technology. And if you've kept up with Moore's Law, this stuff is getting better and better and better. In fact, the infrared detectors, I believe, kind of outpace Moore's Law. But with this particular detector, they also put some electronics inside that thermos. And that's to help with the noise and the readout of these electronics and make it even more sensitive. So here is Masami Oichi. He's a I won't say he's a professor, but he's a doctor in astronomy, and he works at Subaru. He's one of our collaborators from the Subaru telescope, and he has in the past used an instrument called MORCS. MORCS is similar in MOSFIRE in that it's an infrared instrument. It can actually take multiple spectra of objects in the galaxy, but its disadvantage is that it has to use these cookie sheets that slide into the view, and so the instrument actually gets warmed and cooled, or at least a portion of it does, and it can only use so many masks, and so there's a lot of overhead with it. But more importantly, it's not even sensitive to one observation. So this is the same object, and I don't even know what this exactly is. But here's the spectra that was taken with MORCS. And this was some work that was done by Jonathan Trump and one of our former support astronomers, Greg Worth. And they compared the Subaru results to the MOSFIRE results. And what took Subaru 5 hours, we did it in a half hour. So again, because of the detector technology, we're 10 times more sensitive. Fantastic. Oh, everything's golden. No problem. This technology is so cool with the detectors, which we're actually upgrading some of our other instruments. So OSIRIS is due to be upgraded with the detector technology in the coming years, and it's going to be about a factor of 2. And we're actually proposing to do the same thing with NIRSPEC. And in particular, we don't need to look at this in detail, but over here at the faintest objects, we're going to get an extreme increase in the sensitivity with that instrument. So that's something to look forward to. But in the end, I want to express is some sense a direct result of the MOSFIRE instrument. So now we're going to talk about a little bit of the CSU and a little bit of CSU math. But as we're talking about the math, you can concentrate on the right. This is how the CSU moves. It's got 46 pairs of bars, and it does this global move. It moves the right-hand side of the bars into beam. You can see certain slits dropping out as it decides that this is where it wants to put the edge of a slit. And eventually we're going to see the right-hand side moving. These are the coarse moves of the instrument. This process takes 5 minutes. So when you're on Sky, and if you have a lot of masks, 5 minutes is a lot of time. If you only have one mask like Brad did, or Richard Ellis, this isn't a significant amount of overhead. But now you can see some of the slits starting to form. This is only the coarse move. Now eventually it's going to start making these slits even smaller. You can start to see one at the top. You're going to start to see them get smaller. But essentially every night you're getting 3 science masks, 3 alignment masks. You've got a couple of calibration fields. You've got a long slit in there. On average, maybe 12 masks a night. That's really a lower limit. 150 nights a year. We're doing this at least 1,800 times, maybe 2,000 times during the course of a year. So that can be time consuming. You can see it's almost done. I've actually sped this up to be about 1.5 minutes. We can see all these things starting to form. This is what I would call the Ferrari slits at the Keck Observatory, because you can size those slits, so the widths are dynamically changeable. So if the seeing how bright or how blurred out the star is during the night is actually a little bit worse, or if it's really much better, you can fine-tune those slits in real time to get better science or more sensitive science out of it. So that's part of the fun with that instrument. Now, every year, I have to get in front of the Science Steering Committee and talk about MOSFIRE. I have to tell its good things and its bad things. Hilton said I had to talk about some of the bad things, so here they come. I didn't think I had to, but I'm going to. In fact, I believe this is what the Science Steering Committee actually really likes our talks, and I think it's because we're refreshingly honest about the good things and the bad things going on with the instruments. So let's keep in mind that MOSFIRE is doing great. It's 10 times more sensitive than anything else in the universe, or at least on the planet. But we've got some areas where we can do better. I want to make it go up to 11. So here's the first graph I showed on the progress of MOSFIRE, and we're going to talk about this guy right here. This is the time lost to CSU, or the slit mask's errors during the night. And this is just an image of me. I'm talking, I'm giving a presentation to all these real bright, intelligent astronomers who are giving us guidance on where to move it, our next steps at the observatory. So the CSU turned out to be our largest tentpole. And those errors, there was a lot of, I would say, anecdotal evidence that suggested we could operate it in different ways. So Ian and Chuck, in order to get the CSU to move properly, they would first power cycle it. Then they would send the positions. Then they would move it. And then they would observe. And so that was there. And they said it would work for them all the time. We implemented those methods, and it didn't quite work right. But after 5 months of operating this instrument, we found that there are some bad places in which we do not want to move the CSU. This graph here on the right is showing us where all of our problems occurred, and essentially, that is when the rotator, so this instrument rotates on the sky, was at 0 or 180 degrees. We made masks at all kinds of different rotator angles, and that's what all that blue is. But again, at night, our failures were predominantly at 0 and minus 180 degrees. So let's avoid those angles. Why not? So this is what the support astronomers did. We have a whiteboard. And for the first year, we drew this picture. We got a nice circle. We've got CSU stamped on top of it. We've got 0 and 180 degrees and this red no on there to help everybody figure it out. They didn't always figure it out. You can see here we've gone from 600 minutes or 700 minutes to about 60 minutes. This is about 100 minutes. So we've cut the time down significantly just by avoiding that angle. This isn't to say we understand the problem and what was happening. And I'll say this, the bars themselves, this is very interesting, I think, as an instrument scientist. The place where the bars have the most failure, so that's 0 and 180 degrees, is when the bars are moving horizontal to the ground. All the builders, so CSAM and Ian and Chuck, they all thought the hardest way to move these bars was in this direction, and that's because gravity is kind of pulling them in a certain way. They didn't think this direction, this was supposed to be smooth. So that was something that we interestingly learned about the instrument after it got on the sky. And what later on we did is we put this information into the software based on all the success, and we told observers if they were about to move, do you really want to do this? In some cases they had to, in other cases they didn't. But that knocked the time down to 0. I am so excited that I get to tell the SSC this. They're going to love it. So, this is important. Making sure the CSU works is very important for this guy's work. This is Tuan Do. He's one of our astronomers who is ideally pursuing science that was MOSFIRE's second science case. And that was to look at things that you can't see in the infrared. or you can't see in the optical. So this is this position on the sky of the same two locations on the sky, once taken with an optical detector, and another one taken with MOSFIRE. And you can see that there's star clusters in there and a lot of gas and dust around them that you can't normally see with an instrument like LRIS or DEIMOS. And so his project is to understand these clusters that are only about 1 million years old. So we've gone from the 6 million year old age of the universe to present time in terms of what MOSFIRE studies. And MOSFIRE covers a lot of ground. So just to give you an idea of what he's dealing with, this is an observation, this is a little science case of IC 348. IC 348 is a star-forming region in the constellation Perseus. It's located among a string of knotty dark clouds, and you can see those dark clouds here and here. There aren't a lot of stars there. And it's got a bright star which is illuminating a lot of gas and dust in there. Oops, went away. Here's a blow-up of that region. And in particular, these are all the stars that are associated with that star cluster. This rectangle represents MOSFIRE's field of view. So in order to study all those stars, you got to create a lot of masks. So unlike Brad, who only did one mask, Tuan now, and I in particular, have to cover a lot of ground, a lot of area. There are approximately 350 stars there. This is one of our nearest neighbors in terms of star clusters. And so we had, at the observatory, had to build software in order to make this happen. So MOSFIRE motivated an improvement in how we do this. So here's a, can you guys guess which one's the right stars? This is a mask. You can see there's some boxes around here. We want to put those boxes on some stars. This is a very dense field. This is a globular cluster. I was once presented with this challenge, and I didn't know I had it in there until they actually started taking spectra. But this is some work that we've done in preparation for MOSFIRE. Essentially what you do when you get on sky, the observers, what time is it? The observers are probably aligning their first mask right now with MOSFIRE, and this is what they're doing. They're pointing their object to pointing the telescope to the field. They're seeing stars, but they've got their alignment boxes and slits on their mask. The first step is to get stars inside these square boxes, and then they derotate the field, and then they translate the field in order to make sure that you got stars in the boxes and stars in your slits. Simple. And yet, if left to the observer's own demises, they struggle mightily. They do all kinds of things. Until we built some software, they would get the wrong coordinates. They'd mistype coordinates. And to be fair, it's not a Kassis presentation without something misspelled. So I got something in there. Hopefully that's the only one, and that's on purpose. But they'd have the wrong position. Sometimes I'd ask them, do you guys have the right mask? Oh, they'd say. We've got to change that. So this software was designed to help them, and it pretty much has. We've created it such that the software that the observatory staff put together has minimized the amount of time to about 10 minutes. And then we deployed it not only to MOSFIRE, but we gave it to both LRIS and DEIMOS. So both those instruments now are functioning as efficiently as possible. We don't have statistics for MOSFIRE, obviously, because the software was deployed. But for LRIS, we wound up saving about 5-10 minutes of time every slit mask alignment. So that was quite significant over the number of masks you do and the number of nights you have with those instruments. So here's our smallest or youngest observer, Lily. I don't know how she made it in there. She did 10 masks in about 2 1/3 night, and after that she couldn't take it anymore. She went to bed. We also did that IC 348 project, and we invited the HPA astronomy students to come in and take part of it. And so this is Jerry Bleckel and 2 students from his astronomy class. They were great. But, and I don't want to say that I've dumbed this down so that the observers don't have to really think about it, and they're so bad at it that they can't do it. But the point here is that their time is really, really valuable. We want to make things efficiently as possible, and quite frankly, they have better things to think about. They don't need to be thinking about this stuff. Let's make it easy for them. So here's what we did with those HPA students, actually. we have a mask, and we started marching our way through the field. So you can't do this with any other instrument. The instrument is fantastically quick and nimble. It allows you to canvass this area. You can see the date going by here. We were in November, now we're in December. This is in 2013, I believe. But we covered approximately, out of the 350 stars in 2 nights, we've got spectra at all the colors that MOSFIRE could do, essentially of 300 of those stars. So it's a testament to how quickly we can observe and align masks. Very quickly, I know some of you have seen this before, but when we take data on sky, this is what MOSFIRE data looks like. This is the raw data as it comes out. These represent starlight from my data. These vertical lines are the emission from the Earth's atmosphere. The Earth contributes quite a lot to this, and so what happens is that we take 2 positions with our telescope and we image those stars. So here we can see those stars moving in those slits as we bounce back and forth between 2 positions. When we subtract those 2 positions, we then get this nice pair of traces here of the star, and we're able to see things we can't normally see. So in particular, you can see this spectrum right here, or this slit set. When we do the subtraction, we can actually see what that object looks like. So that's a brown dwarf in this star cluster, and this is what Greg Mace has been studying. When we look at this star itself, this is kind of the science what we've been getting with this instrument. This is an M-class star, but these lines right here are an indication that there's a disk around it and that there's material infalling on that star. So that's some preliminary science with that star cluster. We're going to shift to a history buff. This is Richard Ellis and his team. He likes to look in the dark ages. I think that's maybe it's his English background that gets him there. I also collect a few autographs. I'm a fan. He likes to look back at things very, very early in the age and the history of the universe. And so this was a Time magazine spread. Oh, look at here. This is Tucker. Tucker likes to be relaxed in remote ops 1 and 2 when he's observing. He's got little duckies on his, rubber ducks on his pants. I love that. I have one observer who's actually, she's very superstitious. And one time she showed up in a dress that she had made. It was really cool. And it had a solar system scene on it. She had used it for some astronomy party. And then after the party, she was observing, and she wound up getting great data, so it became her lucky dress. So every time we see her, she's in the same dress. Richard Ellis, of course, redshifted to an earlier epoch. But here's what he does. He has used MOSFIRE to find the most distant galaxy in the universe. And he's also setting limits on when these galaxies form. So you saw nice spectra where the stars were easily seen, nice trace. Can you even see it in here? This is his observation with MOSFIRE. This is a subtracted pair. This has gone through our data reduction pipeline. This is tough to see, but this turns out to be, if you do a crosscut, if you just drew a line and sampled the emission along this axis, this is what the spectrum would look like. Here's the peak, and he's pointing it out. He's published this result now. This is what we consider a very 99% confidence level. And he's finding this thing out of a z equals 7.62. That is a galaxy which is formed 13 billion years ago. To be specific, I had to write that down, 13.2 billion years. So he's setting the limits on when this can happen. But of course, he's finding not only things about the science, he's finding all kinds of things about the instrument. And one of the things we found out about the instrument was that when we were nodding the telescope, so we mentioned we have to go to A and the B, sometimes it would go to C. And we thought, well, that's interesting. Turns out if we just reset the observing program, we could fix that and it would go back to doing A and B, but that was a problem. Worse, sometimes it would nod itself out of the slit. That was bad. Now we're losing half of our signal. This didn't happen very often. This happened about once every 3,000 nods, so about once every 3 nights. It turns out that this this problem in particular was a problem that the telescope wasn't listening to what the instrument was telling it to do. So the instrument was saying, hey, I want to move. But the telescope was saying, I hear you. But it didn't move. So MOSFIRE, in this particular situation, helped us solve a long-standing problem. That was not only inherent with MOSFIRE's communication with the telescope, but with all of our instruments. This was great. And we were able to do this because MOSFIRE nods so frequently. It's the one we nod essentially every 2 minutes. So we're doing, what is that, 30 nods an hour. This other one I dismissed due to weather. I'm not perfect. But essentially, what they were telling me is that their star, as we watched it in a slit, was kind of drifting along the slit. It was a bad night. There was clouds. There was telescope problems. I thought, Matt, I wrote up this nice report. It was 3 pages long. Enter the the MOSDEF team. And some of you may have heard these people talk. These guys are doing some science which they're trying to map out the galactic growth at various epochs. And essentially, they're watching galaxies grow when it's very early in the universe, the galaxies getting bigger in the universe, and then watching material get cycled through stars and be formed from the very first stars, which only had hydrogen and helium in them, and there's heavy elements. So things grow. They're looking at the growth of galaxies and black holes. And I'm not going to go into the details of that stuff. The MOSDEF team is looking at 1,500 galaxies in 44 nights. This is an epic observing program. Most people get, anywhere between, sometimes it's a half a night, sometimes it's 3 nights for a semester. These guys are getting 44 nights over the course of 3 years. And they're studying stars at Ziegel 2. Mariska was actually at the Kahilo recently and gave a nice talk about that. But here's some of the MOSFIRE DEF team. This is Naveen, this is Alice, Allison, Brian. I've seen them as graduate students. They're now all professors, and they have graduate students. You can actually see the observing traits being handed down from generation to generation. It's cool. And then they presented me, of course, with this. These are drifts of stars in their masks. I was totally wrong. Not only did they, they've got 44 nights, so they got a lot of data. So now I have to go back to the Science Steering Committee this year and tell them I got another issue I got to solve. But fortunately, I've been studying this for the last couple of months. I have a clue. I have found that the instrument, this thing is drifting as a function of the telescope as it moves, as it points up in the sky, and as the instrument rotates. So hopefully, we'll be able to correct for this and improve our efficiency again with the instrument. So we're making strides to improve this instrument every single day. So the last science case I'm going to talk to you about is Brett. And I love Brett's selfie. Brett is what we might call a proto-PhD. He's 2 years into his PhD program. He's getting some help from these two guys. This is Avi and Daniel. And Brett is watching a planet move in front of a star, and he's trying to figure out what is in the atmosphere of this planet. When Ian and Chuck and everybody else was designing the MOSFIRE instrument, under no circumstances were they thinking that a guy like Brett was going to do something like this. Not a chance. It's not in the science cases, and when Brett first came to me and said he was going to create not these Ferrari slits, but what I am now calling the Winnebago slits, and just look at 2 objects, I'm like, Brett, you're killing me, man. You're killing the efficiency of this instrument. We can do more than just 2. But no, he's serious about this. And the reason why he's doing just 2 is that these 2 things are extremely bright. These things are basically what we could see with our naked eye. These are about 6th to 7th magnitudes. When we look up in the sky and we look at the Pleiades star cluster, you can see stars that are anywhere between 2nd magnitude and 6th magnitude. These things are some of the brightest stars in the galaxy, and we're using Keck to look at them. The reason why he's doing that is that he needs a lot of signal and noise because this star, in comparison to the planet, is really, really bright, and he needs to sample this signal. So when he's doing this, he's watching the star pass in front of it, and the dimness of the star dips a little bit, and based on the shape of that dip, he can actually figure out something about the atmosphere of the planet. Fabulous. The second star is just a reference star, and that reference star is there to watch all the aberrations from the atmosphere. So he's essentially monitoring weather conditions with the other star. And this is what he's trying to do. This data up here on this plot, this is at optical wavelengths, this is Hubble data. We've got some Spitzer data down here, and then there's this paucity of information in this area. We don't need to go into the specifics here, but all these various lines represent different models for the planetary atmosphere that he's looking at. MOSFIRE fits in perfectly, especially H and K band. You can pick out different wiggles in some of those atmospheric molecules that might be contributing to the planetary atmosphere. So here's what he's found. Here's his observation of WASP-6. You can see he's got this nice dip here. This represents 1/30,000th of the signal from the star. When he nods the telescope, he's nodding the telescope every 10 seconds. And he's looking at this object all night long. He's got this nice spectrum. We don't need to go into the details, but what's interesting is that this is not flat. His data comes up as we go from short wavelengths to longer wavelengths in the K band. So he just presented this at an American Astronomical Society meeting in Seattle. What was it, last week? Isn't that right, Hilton? Last week. I'm getting the confirmation from Hilton. He's very excited about it, and the reason why he's excited about it is that if he shifts his data, so these two, there's clearly an offset here, but if we look at this and shift it up, we've got a nice agreement here with this planetary model, and this is telling us that there's actually methane in this planetary atmosphere. This is spectacular work. I am pretty sure that in a couple of years, his proto-PhD status is going to be official PhD status. But until then, I'm glad that he's presented this, because that means he's going to be coming back and doing more of this kind of research. And I, of course, like repeat customers because that's less work for me. So this is pretty, I got one more slide after this, and I want to just end essentially saying that MOSFIRE is awesome, absolutely awesome. And the reason for that is because you have not only this great instrument team, these partners like Ian and Chuck, and all these instrument developers over here, you've got you. You guys are now contributing to this fine institution, supporting us and sharing in these discoveries. Then we've got this great staff. So we've got 40 people here who work on the summit. Uh-oh. So Debbie said I was supposed to be a little bit personal. And as some members of the Keck Ohana know that when I get personal, I get a little choked up. So hopefully I'll get through this rest of this without crying. But anyway, here's the great summit staff. Here's the rest of the guys that work at headquarters. These guys are all experts. Not only are they good at integrating new technologies, but they're great at actually improving them after they arrive. We're never satisfied. Then, of course, we've got this great observing community. They're top-notch. They're producing all kinds of great, wonderful science. And diverse. You got things going on that are, you know, solar system stuff out to the very edges of the universe. But if you want to talk to this little lady, you'll have to wait 15 years. So I'm going to end here with a nice little image that's recently taken by Andrew Hara. And I just want to stress that it's very fun to be a part of the leading science and technology at this observatory. It's great. One of the joys that I have is improving the existing instruments and participating with all these wonderful observers. I didn't make it, Hilton. Wait. I'm going to end with a quote. So, MOSFIRE was, first light was April 5th, 2013. And this is what I put in the night log. This was a very productive night for MOSFIRE. To all the Keck staff who arrived early for telescope reconfigurations every day of the week, stayed late on the summit troubleshooting, interfaced the instrument with the telescope systems, and worked weekends and holidays to make it possible for MOSFIRE to reach first light, you guys are the greatest. So thank you very much. All right, I'm done.
Thank you.